Hi, Kevin. Kevin? You there, Kevin?
Yes, hello.
uh, there are two ways. I'm sorry, there are two ways to be late to some place. One is to actually be running late, and the other is to be early because you find something to do and you get preoccupied. I was answering emails, and all of a sudden I looked up, and it was 9:29. So
Yeah,
that's
yeah, I just saw your other email. I had a question about it.
about what the
The, the pre-lab and post-lab.
yeah, you have until tonight midnight.
Yeah, I went to go and do it, and it's locked.
You
The
should be able to
pre-lab
do it now.
quiz. Okay, maybe it
You should be
reloaded.
able to do it now. Uh,
Okay.
Kevin, I will go in and check afterwards, okay?
All
And
right,
I'll
yeah,
tell
no
you what,
problem.
give me 15 minutes after the after this is over, and I will 15 minutes after this is over, and I will check it. Actually, I'm just gonna hold on. I'm just gonna go and check on it right now, if that's okay with you.
Oh, it just changed.
It
Oh
just
no, that's
changed.
results. No, it says pre-lab and chemical and physical changes ends August 24th.
Okay, pre-lab does.
Yeah.
Okay, I'm in here now. Ugh. Yeah, it ended last night. Today's the 20. Oh, today's the 25th. Okay, you should
Yeah, I
be
went.
good. You should be
Okay.
good now. Okay. Did you do the
Okay.
safety experiment?
No, I went to go. I thought it was all due today at by
No, no, no,
midnight.
no. It's due because it's an online thing. What they did was they ticked all the dates to Sunday midnight to Sunday midnight. So, I mean, it doesn't really matter one way or the other what day is the final day. You just have a week to do it.
Yeah,
Okay.
now that I know, I'll make sure to have it
No,
all
it's
done
not no
prior.
problem, Kevin.
Thank you.
You may be the only person in here today.
Yeah. Oh
It
man.
may be maybe a one-on-one thing. And if that's the case, then what I'm going to end up doing is I'll just play to your needs, okay? And just let me sit here and yes, I'm sorry, I need to get on to. Do you have to get out of here early, Kevin?
Um, no, I mean whatever works for you, as
That's
long
fine.
as I
I just
get a
wanted
grasp
I
of
wanted to
whatever
know if
we're
you had to
doing.
be somewhere by like 11 o'clock.
I'm painting today, so I mean whatever. If you can get through it in 40 minutes, I can leave in 40 minutes. Whatever you want to
Okay.
do. As long as you feel like we covered a
You know,
decent amount
I'm
of
just trying
material.
to at this point. I'm just trying to. I'm going to send out another email to everybody, and people may. I've been having people just fall off because it's not required.
Yeah.
And at this point, Kevin, I'm thinking, it's their loss.
Well, if have you had the recordings? 'Cause I
Recording
went
should be
to
up.
oh
Recording
yeah, I went
should
to
be.
view this. I went to view your second lesson to redo some of my notes, and the link wasn't like a link; it was just an HTTP. But if you got that figured out, I mean, you can avoid this 9:30 thing altogether just by
Okay, let's
having
see.
people watch it on their own time.
Well, that's true in the fact, but I still have to do it. Yeah, that's. I haven't published them yet, Kevin. I'm sorry.
Yeah,
Wait. I haven't done them all. I haven't done all of the lectures yet.
yeah,
And I'm having trouble with my evening lecture because of the fact that after I end the lecture Zoom meeting, I have 15 minutes to start my lab meeting, which means that that's not enough time for it to record, to upload all the information. So I'm going to have to change that Zoom meeting in the evening to be later.
Okay.
Okay. Did you look at the morning or evening?
I looked at the evenings, the second lecture.
Evening?
Yeah.
This may be what the problem is. Okay. The
Maybe
second
try
lecture
the
should have been.
morning.
Okay, you downloaded the Word document, right?
Let me see here.
You have to download the Word document instead of just opening it.
Okay. You download it, it works.
Yeah, eventually it works. Okay.
Yeah.
Okay, and I'm just gonna. I'm trying to work this through.
No worries.
It just uploaded for me.
I'm checking it out now too.
Okay,
Oh, yeah. The morning one works.
The morning one, I just tried the second evening one, Kevin.
Yeah.
I just went into the second evening one and it worked. Okay.
Okay.
All right, I'm not going to go through the Jabberwocky thing. If you're the only person here,
I kind of skipped that when I was looking too. I wasn't sure what that was about.
What it's meant
like,
to do is it's meant to kind of like freak you out and try. And basically, these are absurd things, right? And I don't know if you had the good one or the bad one. Are you seeing the screen now?
Yeah, I can see it.
Okay, basically, what I go through is I say that, say the thing, and basically I give you all of these conversion factors of nonsensical things, and you have to tell me if you have 5 Fermius Bandersnatches, how many Jabberwocks. So I basically, did you see, is this the one you saw? Where they have this thing?
I went through this whole slideshow already on my own.
Okay. How do you feel about it then?
I felt like it was mostly review.
That's what it's supposed to be. Are you comfortable with doing dimensional analysis problems?
Yes, yes and no. I'm comfortable with running them out, but sometimes I have a problem with setting them up properly.
Okay. Do you write the labels down, Kevin?
Meaning, just labeling each numeric.
Like labeling the Tulgey Woods, the Bandersnatches, the Tum Tum trees, the Tulgey Woods. Are you not putting labels there?
I definitely label them all. My biggest problem is I'll like skip one conversion. So I'll have all that written out, but I'll leave one of them off and then I'll get the wrong answer. But that's just me.
Part of the thing is if you do the labels, you'll know that something's missing.
Yeah.
Okay.
I think it's just with practice. I'll be pretty fine with that.
The dimensional analysis problems I have that are the extra homework, those are pretty good. How did you do on the quiz?
I think I got a 90%.
Okay, I'm going to go in and let's see. I'm going to try and screen share.
The extra homework's just for practice.
It's just for practice. You're not getting graded on that.
Okay, I'm making a note to check it out.
Am I in L or am I in? This is L. Yeah, this is the right one. Okay. I actually have to do this anyway, so I'm going to go through this problem on the quiz we had today, all right? Somebody asked me a question on it. And who knows, I might very well have given the wrong answer. All right, got to find quiz 2. There we go. Are you seeing the screen now?
Yeah, I see it.
All right. Okay, we're going to go edit. It's the easiest way to me to get here. Properties are.
Oh yeah, I remember the rum and coke.
A rum and coke.
Oh yeah, the rum and coke question was cracking me up.
So I have to.
That one, it just cracked me up. I'm pretty sure I got it right.
Okay.
I was just laughing when I read it. I was like, oh, I think I'm gonna make a drink now.
There you go. Okay. Tell me how you set this problem up.
This one I just did 40 times 3 for 120 slices, and then I divided 120 by 8 for total number of slices, and then multiplied by $7.99, and that was over $100.
Okay. Okay. So basically, I'm looking at this problem, Kevin, analyzing this problem. I want to find out the dollars it's going to cost me, right?
Yeah.
So I'm going to put the equals dollars on the right side of my equal sign. Now, what am I given? Okay, what am I given? Like you said,
given, yeah, students, slices.
you're given, you have 40 students. And so that's what you're starting with. This is 40 students. You got to feed 40 students, right?
Yeah.
How many slices can each student eat?
3.
So you got 3 slices over 1 student, because that's the conversion for that, right?
Yeah, I didn't see that it was $7.99 for 2 pizzas. I thought it was for 1 pizza.
Ah.
That's all. That was a mistake I made.
All right. So let's just keep on. I have to do this because I have to justify it to somebody else. Okay. So our next, we've gotten rid of students. We now have slices. So for 1 pizza, there is 8 slices. So 1 pizza goes on top, 8 slices goes on the bottom. And we have $7.99 for 2 pizzas. So basically, as you said, you got 40 times 3 times $7.99. That equals 958.8. I got to divide that by the 8 slices, divide that by the 2 pizzas. That ends up being $59.93. So yes, you had enough.
It tricked me. I guess my mind immediately assumed that $7.99 was 1 pizza instead of 2.
Perhaps it was unfair, and
no, I think it's fair. I just didn't read the question correctly.
What's unfair about it is the fact that I've got all the numbers except 1.
Oh,
so you see what I mean? That's
yeah.
In a way, it was a bit unfair because all the numbers except that 1 were in number form. That one was in a word form. I apologize about that, but you still should have gotten it from the pizzas.
Oh yeah, no, that's my fault.
All right.
The one question that I messed up was the density of chloroform has a solid mass. That one is the one I got wrong, and I got them as the same mass, so I thought that if it's the same mass, it would be suspended.
Okay. How did you do this?
what did I do? Let me see if I can find my worksheet. So if I took the mass of 3.31 times 10 to the negative third pounds, and I converted that to grams, and then
With
I
what number?
converted pounds to grams. I did
454 or 453.5. You can use either one.
I think I did 453.5. Let me see. I know I have the work here somewhere. Yep. I don't know where I put it. Yeah, I don't know where I put my work for it. I probably have thrown it away. But so I basically just converted the mass and the liquid weight or whatever, the gallons, and I got 140. I think I got like 148.9 or 1.489 grams per milliliter.
Okay.
I don't know if I just did it wrong or what.
Okay, the 2.64 times 10 to the minus 4 gallons times, first of all, you got to go 4 quarts to a gallon. Then you got to go 1 liter for every 1.057 quarts. All right, times 4 equals divided by 1.057 equals. Oh, then I got to do 1,000. Okay, the way I came out with it was I got the 3.31 times 10 to the minus third pounds times 453.5 grams per pound. That gets me 1.50 grams. Okay?
You did it multiplied by what?
I multiplied it by 453.5.
Okay, yeah.
To answer this problem, it doesn't matter whether you use 453.5 or 454. Okay?
Okay.
Then I multiplied 2.64 times 10 to the minus 4 gallons times 4 quarts per 1 gallon times 1 liter per 1.057 quarts times 1,000 milliliters per liter. And I got that answer to be 0.999. So I divided the 1.50 by the 1.99 and because the density of the solid is greater than the density of the chloroform, it will sink to the bottom.
So one point, hold on. The 1.50 divided by 1.99.
No. 1.50 divided by 0.999.
Oh, okay. Which is, it's slightly
heavy. It's slightly more dense than the chloroform. Since it's slightly more dense than the chloroform, it will sink to the bottom.
Yeah, I must have been I must have been off just a little bit in my calculations. I somehow got 1.49, but that's okay too. I'm just glad I understand that if it's heavier, it sinks, and if it's lighter, it floats. If it was suspended, would it be the same?
Yes.
Okay, that was what the clarification I really wanted.
Okay, I've got another person coming in, Kevin.
All right. Okay.
All right. Angie?
Hey, Mr. P.
Hey, Angie. I've only got 2 people in here, so I'm kind of like doing it. I'm kind of doing it freestyle. All right.
Okay.
And for the last 20 minutes, I've been talking about dimensional analysis problems. Do you have problems with those?
I don't think so, no. Like converting and stuff, I don't think I have any.
Okay. For example, do you see what's on the screen right now? The quiz question?
Yes.
You tell me how you'd answer this, Angie.
Okay, let me figure this out.
Angie, talk your way through this problem.
I don't know. I don't know if I know how to solve this one actually.
That's fine. I don't know is a perfectly good answer. All right, right now you have pounds and you have gallons, right?
Yeah.
That's what you're given. Well, you need to compare it to grams over milliliters. Okay?
Yeah.
So basically what you have to do is you have to turn the pounds into grams and you have to turn the gallons into milliliters.
Okay.
Then you're going to divide the grams of your solid by your volume of your solid, and that will give you an answer in grams per milliliter. Then you compare it. If the answer you come up with is larger than 1.59, then it's going to sink. If it's smaller, it's going to float on the top. If it's the same, it's going to be suspended somewhere within the liquid. Okay?
Okay.
So how do you go from pounds to grams? Do you know what the conversion is?
From pounds to grams.
Yes.
So, well, okay. So the density is grams over milliliters. You want to have, when you convert from grams
You
to
have pounds. You have to convert pounds into grams.
Yeah, you would have grams on the bottom so that the grams would cancel out, and then pounds on the top.
No, Angie, you're starting off with grams. Okay. Let me see. I'm going to stop share here. Let me get the vital information. Oh, I got it. All right. Stop share. And somewhere, there's supposed to be a whiteboard on here. Can't do that. I'm supposed to have a whiteboard on here and I don't have it right now. At least not that I can see it. Okay. Well, we'll go with this, okay?
Okay.
All right. You see this? Are you seeing the Jabberwocky screen?
Yes.
Okay, what I'm going to do is I'm going to go into here and I'm going to make up a new thing, okay? So I have 3.31 pounds. That's what I know, right? What I want to know is grams because I need to change this into grams per milliliter. So if I want to get grams and I want to get rid of pounds, what goes on top, Angie? Angie?
Oh, sorry. I thought I was okay. Sorry. Pounds have to go on the bottom and grams have to go on the top.
So you're going to do grams divided by pounds.
Yeah. Sorry, I was explaining it and I didn't realize I was on mute.
Okay. So do you know what the conversion is?
Well, grams over pounds, right?
Yeah, but what is the actual number? How many grams are equal to 1 pound? You know it?
No, not off the top of my head.
453.5 is equal to 1 pound.
Okay.
So if I do this math out, then I end up with 1.50 grams.
Okay.
Okay?
And I think that was bigger, so it'll sink.
Now, this is just grams.
Oh, okay.
The other density was in
yeah.
grams per milliliter.
That's
So you have
right.
a second part of this problem. And the second part is
It's in gallons.
2.64 e to the minus 4 gallons. And you want to eventually have,
Milliliters.
so I'm going to put the milliliters on the right side of the equation. Now, what's the easiest, do you know of any conversions between between English and metric in volume?
Yeah, I think there's 4 quarts in a gallon.
Okay, so what's going to go on top, Angie?
The quarts are going to go on the top and the gallons are going to go on the bottom.
Okay. All right, so I've got now my gallons have canceled.
Mm-hmm.
I got quarts. What do you want to change the quarts into?
Let me think. Well, I know that there's like 16 point something cubic centimeters in a cubic inch.
Okay,
So,
let's go simpler, okay?
Oh, okay.
All right. Eventually we have to change English to metric, okay?
That's what I was trying to go.
I understand. If I tell you there's 1.057 quarts in 1 gallon, quarts in 1 liter, would that work for you?
Yeah, that works.
So what goes on top there?
The quarts goes on the bottom, the 1.07 quarts, right?
No, it's 1.07 quarts to 1 liter.
Okay, so yeah, 1.07 quarts goes on the bottom, and then liters is on the top.
Okay.
And then it's easy from there. So the liter goes on the bottom, and 1,000 milliliters is on the top.
You do all this math out, and I'll check myself again. I get 0.999. So to find the density, I got 1.50 divided by 0.999. That equals 1.50 grams per milliliter. Okay. Angie, you got a good sense of how to do dimensional analysis problems.
Okay.
Right now, what's happening is you don't have the conversions, and those will be given to you, okay?
Okay, great.
So I feel confident both of you know this information.
Okay.
Yeah, I think I'm good too.
Okay, we good with that?
Mm-hmm.
So
Yeah.
I'm going to stop this. If you do as I told Kevin earlier, Angie, do the homework problems that are extra. The
Okay.
extra homework problems probably are a better idea of how to do dimensional analysis problems than the mastering. Sometimes mastering is adequate. This is an occasion where it's not really, okay?
Okay.
All right, so let's pull up the second PowerPoint I had, which is matter. You guys seeing the screen?
Not yet.
No.
Okay. Now you're seeing it.
Yep.
Okay. I'm going to go through this really, really, really quick. Okay. Because basically you've had this crap since you were in 7th grade. I just need to know that you understand what's going on. All right.
Okay.
Basically matter has two properties, 2 characteristics. What are they?
They have
Matter. What does matter have?
Mass and take up space.
has mass and volume.
Oh,
So same thing, takes up space. Angie is the same thing as saying volume. Okay? And basically you have matters composed of elements. And if you really go down to the most basic form of an element, you can chop it down further and further and further until you get to an atom. And an atom is the last particle that will have the properties that the element has. Fair enough? You chop
Yeah.
up an atom anymore, and you do not have the properties of the element anymore. Yeah, just went through that stuff right there. So states of matter, yeah, I know there are, you get into plasma, and what else is it, superplasma? We're not going to deal with them. We're dealing with chemistry. Chemistry doesn't really deal with plasma. That's a physics matter. So the three states of matter we're going to be concerned about are solids, liquids, and gases. And really, solids are basically tightly held atoms to one another. They may vibrate, but they don't move. Liquids, the atoms are kind of sliding over one another, which means that they can flow. Gases, they basically have nothing really to do with one another. So what I really want you to do, I'm going to go out some slides forward here. You can read this if you want, but the real slide I need you to know is this one. Solids hold shape, have the same shape, have a fixed volume. Liquids take the shape of the container, they have a fixed volume. Gases, you have the shape of the container and the volume of the container. All this stuff you've had before, right?
Yeah.
Like many, many times. Now, basically, if all the atoms in the sample matter are the same, you have an element. If you have different atoms that are combined together and you have a pure substance, you have a compound. So pure substances are composed of elements and compounds. Now, when we have a compound, we have something called the law of definite proportions. That means no matter how you come up with that particular molecule, it will always have the same mass proportion of one element to the other. In the case of hydrogen, you will always have 2 grams of hydrogen. In the case of water, you will always have 2 grams of hydrogen to 16 grams of water. In the case of ammonia, you will always have 3 grams of hydrogen to 14 grams of nitrogen. And ultimately, when we start to get into moles of things, what it comes down to is you have the same number of atoms of one of the elements to the other when we're in the law of definite proportions. So it was developed by Joseph Proust. It means that the ratio of atoms in a compound is always the same. If we have methane, that means we have 4 hydrogen atoms to 1 atom of carbon. We good with that?
Yep.
Okay, we can classify elements and compounds as pure substances, so it can be an element or a compound. Silver, Angie, element or compound?
Element.
Table salt, Kevin. Kevin, element or compound? Kevin's gone away for a second. Angie, element or compound?
Compound.
Okay. Basically, if it has more than 1 element in it, we've got a compound.
Mm-hmm.
Now, if you combine 2 elements or compounds or a compound and an element together, what you get is a mixture. A mixture has 2 of the more pure substances put together. But when you have a mixture, there is no defined ratio. You do not always have the same amount of one element or compound to the other. So if you have salt water, you have sodium chloride and you have water. Now, Angie, if you're making pasta water, is the salt water a little more dilute than if you go sucking water out of the ocean?
Yes.
But they're both mixtures. So when we define a mixture, we have to define not only what is in it, but we also have to define how concentrated it is, how much of it is in there. Make sense?
Yeah.
Kevin, you're back, right?
Yeah, sorry, I had to go to the bathroom.
No, too much information, Kevin.
Okay.
Mixture or pure substance, Kevin? Bronze.
Pure.
It's a mixture.
Oh.
When you do bronze, you do copper and zinc, I believe.
Oh.
Okay, so you just put the two metals together and they mix up and make a mixture. Copper wire, Kevin?
Pure.
Very good. Air, Angie?
It's a substance. Or
What's in air, Angie?
a lot of elements.
A lot of compounds. Remember, hydrogen and oxygen are diatomic. They're molecules.
Oh, yeah, so it's a mixture.
Okay, so we have nitrogen, we have oxygen, we have carbon dioxide. What is air, a mixture or pure substance?
Mixture.
There we go. How about a gold ring, Angie?
It should be pure.
If it's pure, you're not going to put it on your finger because it's going to bend like crazy. That's why we have 24 karat is pure gold. Normally speaking, when you have a gold ring, it's generally around 16, 14 karat. So
Okay.
there's other stuff mixed in with it. How about a Mai Tai?
I don't
Mixture.
know.
Are you old enough to have an adult beverage?
No.
Sorry. Got 3 years to go. Kevin, a Mai Tai, mixture or substance? Pure substance.
Mixture.
There we go. Now, they can be homogeneous or heterogeneous. Basically, if it's homogeneous, you can't tell the difference when it's mixed together. Heterogeneous, you should be able to see the individual items that make up the mixture. So if we're looking at a homogeneous, when you put the salt in the water, can you tell there's salt in there just by looking at it?
Probably not.
Not unless you put too much in there.
Yeah.
So if you can't tell, if it's uniformly spread out, then it's homogeneous. On the other hand, if you have a pizza and you hate olives and you hate mushrooms, are you able to pick the olives and the mushrooms out of a pizza?
Yeah.
Most certainly I have a personal experience with that. Anytime I get a pizza with mushrooms or olives, I pick them out. Gas and water. You have a soda pop, you have a Coke. Is that homogeneous or heterogeneous?
Hetero.
Agree, Kevin?
No, I think I disagree. I guess you can see the bubbles, but that's only when you shake it. I don't know.
Again, Kevin has pointed out something. If I give you a question like this on a test and I happen to mark it wrong, if you come back to me with your logic like you just did there, Kevin, I'll give you credit for the point. Because if you just have a Coke out, if you, Angie, have you ever seen like a 2-liter bottle of Coke that hasn't been shaken up that's there? Can you see the bubbles in it?
No, you can't.
Open that bottle up. You can see the bubbles, right?
Yeah, because there's carbonated
This could be
water in
both.
there. Oh, okay. Okay.
So we're both right.
I'm
Yay.
sorry? A vodka martini.
I don't know.
Homogeneous.
Probably homo.
Don't you put olives in a martini?
Oh, no, I don't.
No. No.
I don't even drink it, so.
Oh, yeah, you're snitching on yourself.
Well, basically, again, I may mark the question wrong on the test, but if you come back to me with your logic, you may get the points from that. A pizza we've already discussed. How about bread dough?
Homogeneous?
Yeah.
I'd pretty much say homogeneous. Now, when we're dealing with liquid mixtures, we have special terminology. Instead of calling something homogeneous or heterogeneous with liquids, we use two different terms. One is miscible, and miscible kind of sounds like mixable, right?
Mm-hmm.
So if you have two liquids that are miscible, that means it's homogeneous. That means you can't tell one liquid from the other. If you have two liquids that don't mix, have you ever made an oil and vinegar salad dressing?
Yep.
You know that if you shake it, you get kind of like some funky little thing going on there, but eventually it separates out, right?
Mm-hmm.
That's a case where you have the vinegar not mixing with the oil that you put in there with it. That would be immiscible. And basically, if you're looking at an immiscible liquid, if you kind of shake it up, you see these funky looking lines in there. But if you let it settle, you will literally, if you look at the liquid, you will see a line that separates one of the liquids from the other. We good?
Mm-hmm.
Yeah.
Yeah. Okay. Any questions about matter?
No.
Then you
Nope.
know what's the matter, Angie.
No. I don't know what's the matter.
Okay. Now we got to get on to the second. Again, literally speaking, guys, literally speaking, a lot of this stuff, I know you've had it before.
Mm-hmm.
I know you've had it before. So that's why I'm literally going through it so quick. Okay. We're finally into chapter 2. You see the new screen?
Yep.
Yeah.
Okay. So, and I'm looking right now at about, what am I looking? About 20 after 10. I will stay basically on here till about 11 o'clock, okay?
Okay.
Okay, topics, the things that I consider to be important. And basically these topics will be reflected on the online outline. Yes, you're going to have to know the history of the atomic theory and structure. We're going to go through the conservation of mass and energy, the structure of the atom. By that, I mean determination of protons, neutrons, and electrons. Guys, that is probably the biggest part of this that I want you to know. We're going to go through isotopes and the average mass calculation. Right now, you know, you have calculations in density, temperature. This will be your third one that I can recall. We're going to go through a basic tour of the periodic table, go through ionic and covalent bonds and nomenclature. That's basically all that's covered in this slideshow. And basically, that is going to be, basically, I'm looking at the next 2 lectures after this. All right. Basically, the atom, as I just said, was the smallest identifiable unit of an element. And the properties of the atoms are going to determine the properties of the matter. Got about 91 of them. Actually, that's wrong. There are 92. 92 naturally occurring atoms. The reason I know that is number 92 is uranium. After that, all the other elements have been man-made. Okay. When we have a charge, it can be positive or negative. They attract. Opposite charges attract, while like charges repel. Nothing you haven't done. You've seen a magnet. This is making sense. Basically, the force that's involved in this is something called Coulomb's law. Coulomb's law says the force is equal to some constant times the charge on the first particle times the charge on the second particle divided by the distance between them squared. And so if we notice this, if the forces are opposite, what's the sign of this going to be, Kevin?
Positive.
If the forces are opposite from one another.
Oh, like, oh, it's,
So one's going to be
negative.
positive and
It'll
one's
be
going to be negative.
negative.
You multiply
Negative.
positive by a negative,
yeah.
what's the
Negative.
force going to be?
Negative.
So it's negative. And if you remember back from energy, negatives mean they're exothermic, right? More likely to happen if it's exothermic, right? On the other hand, if they're positive, if both charges are positive or both are negative, then the force is going to be positive. It's going to be an endothermic force. Way back when, a guy by the name of Empedocles believed matter was composed of 4 basic elements: fire, earth, air, and water. He was opposed by a guy named Democritus, who proposed that matter was made of small individual particles that he called atomos. He basically said that the atomos could be combined in different ways to give rise to all the different substances that we see. And this debate went on long and long until Aristotle. I mean, Aristotle had great power because he was considered the highest of the minds. So Aristotle supported Empedocles. So basically, the atomic theory was not accepted until many centuries later. Robert Boyle, who lived in the 17th century, said basically, he called them elements. And he said basically that an element is something that occurs when you break down an element can't be broken down into simpler substances by chemical reaction. So basically, he came up with this concept of element, Robert Boyle. Proust gave us the law of definite proportions. He's the one that said a compound exactly has the same proportion of the element by mass. Eventually, we know that that is going to be, it has the same proportion of number of atoms within the molecule. John Dalton, in 1808, developed what he called the atomic theory. This is where we're getting into the modern age of chemistry. By the way, do you guys know what scientists were at that point? Was there any profession for scientists? Was there a profession of chemists way back when?
I don't
I
know.
wouldn't think so.
No. I just read a book on Ben Franklin, and it was really, really enlightening. Basically, all these guys that were made famous by science, they all did this as a hobby. Like Franklin got his wealth being a printer, and he only went on the side and studied electricity as a hobby. All these guys did something else. This guy happened to be a school teacher. Basically, his atomic theory says all matter is made up of atoms. All atoms of a given element have the same mass and properties. Compounds are formed by the combination of 2 or more atoms. A chemical reaction is a rearrangement of the atoms. And elements are not arbitrarily converted into other elements. If you remember, at this time, Dalton was dealing with alchemy. And you had all these guys that were trying to turn lead into gold. Dalton basically said that can't happen. So at this point, we're starting to build the field of chemistry. Later on in the century, what Dmitri Mendeleev did was he studied the properties of individual elements. And he basically did some things like he said, one potassium reacts with one chlorine and one sodium reacts with one chlorine. So they must be similar. So I'm going to group them together. However, calcium reacts with two chlorines. So I'm going to group that separate. And magnesium, by the same token, also reacts with two chlorines. So I'm going to keep magnesium and calcium together, and I'm going to keep sodium and potassium. And when he did this, he was able to come up with these groups of chemicals, and he published the first periodic table. Yeah. Another thing he did was he predicted elements. Basically, germanium didn't exist, according to the scientists at the time. He predicted that it did exist, and later on they were doing some studies, I think in Sweden, on phosphorescence. And they found germanium with this phosphorescence thing. It's continued on. Guys, around the turn of the 20th century was the greatest explosion of chemistry ideas that we've ever had. J.J. Thomson, basically, he studied, what he did was he was able to see a beam of electrons. He had a source of electrons on one side, and he had a receptor on the other side. And he was able to see these electrons go through in a stream. Well, he exposed this particular experiment to a magnet. And he found that the beam of electrons was going towards the electron. So basically what he did was he discovered that the electron really did exist, but he also kind of deduced, since when you touch substances and you're not shocked, that must mean there's something that's counterbalancing it. So he kind of deduced that the proton was there as well. What he did was he came up with a model. Now, neither one of you know what a plum pudding is, I'm sure, right?
It's a dessert.
Yeah, it is kind of. It is kind of. Basically, what they do is there's kind of like this mishmash of pudding, this pudding mixture, and you throw plums in it. Basically, the example I'd rather, have you ever eaten a Jell-O salad? A Jell-O fruit salad?
No.
Jeez. I'm distancing myself that far.
Negative.
Okay. All right, just imagine this then. Jell-O kind of suspends things, right? Right?
Yeah.
If you put fruit in the Jell-O, what you do is you put the Jell-O in the refrigerator and you start to let it set. It's not completely set, but it's on the way. At this point, you take the Jell-O out and you stuff things like grapes and small pieces of fruit in there. Can you imagine what this looks like?
Yeah.
Yeah.
This is basically what Thomson said. So basically, Thomson said that the atom was kind of a solid looking thing, solid like substance with the consistency of pudding or Jell-O. And this basically is the device I was talking about. Basically, he also determined that the charge to mass ratio was about 2,000 less than hydrogen. Now, hydrogen is a proton. So that's why that actually is an important development. Okay, again, talked about this. There's another scientist by the name of Robert Millikan. And basically what Millikan did was he was able to determine the charge of an electron from an oil drop experiment. And basically what that looked like, he had a device, an aerosol device that was able to put fine droplets of oil on there. Now the fine droplets of oil, because of gravity, he put these oil in a vacuum. Because of gravity, the oil slowly went down. Then what he did was he had one slit, and between this slit, he had a potential difference. In other words, an electrical field. And that electrical field put a charge on that oil drop. And so basically, he had a positive version down here, a negative version down there, and he was able to determine the change in acceleration once he put a charge on that. Because he knew what the mass of the oil was, he was able to determine the charge to mass ratio. Then we get to Ernest Rutherford, who was a student of Thomson's. And Rutherford was actually trying to prove Thomson's theory. And he was basically saying that, that atoms are full of a mass. It's a solid material. So what I'm going to do is I'm going to take gold, I'm going to heat it up, and I'm going to make something called alpha particles. I'm going to shoot those towards, I'm going to make alpha particles and shoot them towards a gold foil. And basically, what he was trying to do was he was literally hoping that some of these things would not bounce back. But he determined that they did. Basically, what the theory was there's a little bit of space between the atoms, and that little bit of space will allow the alpha particles to go through. But what he found was that some of the alpha particles would hit something and then bounce back. Because when it hit something and bounced back, he knew that there had to be something fairly solid there so that the alpha particles would bounce back. He also had some things that they would hit the side of the solid mass and be deflected. They wouldn't travel in a straight line. But most of the alpha particles went through this in a straight line fashion. From this, what he deduced is that the atom, because most of them went through, he said the atom is made mostly of space, but it does have a solid nucleus. All right, there was a phenomena. There's a phenomena called the electromagnetic catastrophe. Basically, the way we looked at light before this was we felt that light was all in waves. If light is in waves, as you heat an object, then the waves should increase in further and further amounts. But we know that doesn't happen. Because think about when you open an oven. You are not blasted with UV light when you open an oven. Because you're not blasted by that UV light, this means that something is happening that doesn't explain, that the wave theory can't explain. I'm going to get into this more when I talk about quantum mechanics. But basically what Max Planck did was he explained this by saying that energy is emitted in small discrete units that he called quanta. Think of it this way. Before Max Planck, we thought that energy was in wavelength. Wavelengths flow and vary in waves. So you might think of the wave theory as walking up a ramp. What Planck did was he said, well, that's not how it happens. What it happens is we have matter emitted in discrete units that he called quanta. So that's like walking up a set of stairs. Now, we come to a guy by the name of Niels Bohr. Again, I'm going to get into Planck and Bohr much more when I get into quantum mechanics. What Bohr did was he combined Planck's theory and Rutherford's theory. And what Planck did was he said that the electrons were outside of the nucleus, did have a lot of space, and they traveled in specific energy levels that he called orbitals. The energy difference between the orbitals was related to quanta. Higher the orbital, the higher the energy. And yes, guys, you are responsible for knowing these guys and their major contribution.
They'll be on the test or the quizzes or both.
It will. Let me put it to this way. It'll be one question. I'll
Okay.
give you one question and say something like, what did Mendeleev do? How did Rutherford contribute to the structure of an atom? Okay. Simple. I want a simple one sentence. But again, remember, do you have the PowerPoints? If you printed the PowerPoints out, do you have them there?
Yeah, if we printed them.
If you printed them. And other than that, this is not, Tro does not do a good job, does not do an in-depth job going through this as I just did. So just be aware of that fact. New guy, Antoine Lavoisier, developed the law of conservation of mass. By the way, Antoine Lavoisier was an economic, yeah, one of those guys. He was involved in finance for the king. And he lived around the turn of the 19th century. French Revolution happened. He happened to be beheaded because he was a part of royalty. Side note. Basically, he came up with the conservation of mass. And basically it says in chemistry, in chemical or physical changes, no mass is ever gained or lost. It's just moved around. Again, in chemical or physical changes. This does not include radiation, which you will get to in Chem 2. Again, no mass is ever gained or lost. It's just moved around. So what two elements make up water, Kevin?
Hydrogen and oxygen.
Both are diatomic. So basically, the equation for the formation of water should look like this, right? You have H2 plus O2 makes H2O. Why is this wrong?
So you only have one particle oxygen or one part oxygen?
Basically, if this were the way it really happens, then I would be destroying an oxygen atom. Lavoisier said I can't. So what really happens is we get two hydrogen molecules to react with one oxygen molecule to make two water molecules. This is why balancing a chemical equation is so very important. We also have a conservation of energy. Basically, when you do chemical and physical changes, no energy is ever gained or lost. It's just transferred from one form to the other. Basically, what we're talking about is the difference between kinetic and potential energy. Basically, this isn't exactly true because Einstein proved in his theory of relativity that mass and energy were related and they can be interconverted by his famous equation, E equals mc squared. But that does not occur in a chemical reaction. Basically, it may occur. It may occur in a chemical reaction. We just do not have instruments fine enough to measure that. The relationship of the mass lost to the energy gained is so small that can't be measured. Does that make sense to you? It may happen, but it hasn't been proven. Energy basically is just the capacity to do work. And we have kinetic and potential. Potential energy is the energy associated with position or composition. You have the guy in a barrel that's floating down the Niagara River. He has potential energy. He has the potential energy of the distance from the top of the falls to the bottom of the falls. In chemistry, we're more interested in composition. Water has energy. It has the energy that's associated with the bonds. There's an energy associated between both the first hydrogen and oxygen bond and the second hydrogen and oxygen bond. That is potential energy. If we were able to break up a water, we could literally create energy. And as a matter of fact, that happens every time you get pulled over for a breathalyzer. The breathalyzer is using the breaking of bonds to create the energy to come up with a change in energy from a person with alcohol and a person without alcohol. Does that make sense? Alcohol has energy because it has chemical bonds. The person blows into it. He blows into the instrument, and the instrument converts that ethanol to carbon dioxide and water. When it does that, it has created energy, and when it creates that energy, that gives enough energy to light up the LED on the breathalyzer. So it has the potential energy by its composition. Kinetic energy is the energy associated with motion. Basically, as the kid is floating down in that barrel down the Niagara Falls, that is kinetic energy. They can be interconverted. Now, we're going to learn when we get into thermodynamics, which I believe is chapter 7, we're going to get more and more into this. An exothermic reaction is a chemical reaction that releases energy. It's basically you're sweating to try and cool off. On the other hand, an endothermic energy is one that absorbs energy. You have to shiver to create energy to overcome being cold. Endothermic absorbs energy, exothermic will emit it. Okay, guys, we are at 10:45. This is the end of the third day, and I have effectively caught up.
Okay, thank you. Have a good day.
So this means you're not going to be subjected to any extra time because I screwed up the first day for not letting you go early. Yes, I know it's boring. You got basically this is all review. I really don't think you're going to have any problem until we get to the 5th lecture. The next one's going to be atomic structure, periodic table, and valence. The one after that's going to be compound balancing and nomenclature.
Are we going to have these as many quizzes throughout the semester?
Yes.
As we've been having?
Yes.
Okay.
I tried to front load them, Kevin.
Yeah, I was like, oh man, there's another quiz due? I was like, oh my gosh.
I tried to front load them so that by the end of the semester, like between test 3 and test 4, there's only 4 quizzes. 1, 2,
all right,
3,
sounds
4.
good to me.
Between test 1, I've got 5. 5 for test 2.
Yeah, I was just wondering. It's no big deal. I just wanted to
know,
so I'm mentally prepared for it.
Okay. I tried
All
I tried to back off because basically that's the way whenever I'm dealing with the task, I like to do the hard stuff first and then kind of like ease through the rest of the way.
All right. Okay. Well, have a good day. I'll see you
But-
Thursday.
But Kevin,
Yeah.
look at that schedule. Pretty much for the first couple of tests, you're going to have either a quiz every day or a homework assignment due. And
Yeah.
you do have a quiz on Thursday,
27.
and homework 1 is due on
Yeah.
Thursday.
Yep.
Okay?
All right. Thank you very much. Have a good day.
Have a good
Thank
day.
you.
Angie?
Bye.
Angie,
Yeah.
you good? You
Yeah, I'm
understanding
good.
everything?
Pardon?
You understanding everything? Pretty much
Yeah.
review?
Mm-hmm.
Again, I'm going through this stuff very quickly because of the fact that you should have had it before.
Yeah, I
If
had
you-
it like first semester. Yeah.
If you have questions, stop me. All right?
Okay.
All right. You take care of yourself.
Take care. Thank you.
Bye.